Welcome back to the deep dive. You know, for decades, we've been promised this vision of technology that truly deeply understands us.
Right.
Not just what we type into a search bar, but the deep context, the goals, the real intention behind what we're doing on our computers.
It's a very old promise.
It is. I mean,
Yeah.
think back to those foundational visions, the things that really launched the whole field of human-computer interaction.
Yeah.
You have Mark Weiser's idea of calm technology, where, a smart alarm clock doesn't just buzz at 7 a.m.
Yeah.
It knows you have an early meeting, it knows you slept poorly, and it knows the perfect time to offer you coffee.
Because it has that rich historical knowledge.
Exactly. Or Apple's famous concept video, the Knowledge Navigator, showed an agent that was smart enough to just block a phone call.
Because it knew the user was focusing.
Right. It knew they were deep in a complex document and shouldn't be disturbed. These are systems with a holistic, always-on understanding of your life. And yet, you look at the tools we use today, even the best LLMs, the best productivity apps,
They're still so fragmented.
they are remarkably contextually dumb. They just
Yeah.
operate in these frustrating little silos.
Yeah.
Okay, let's unpack this. Our sources today introduce an architecture that's really designed to finally bridge that huge gap between the futuristic promise and, our current fragmented reality.
And what's so fascinating here is that the core problem, both technically and philosophically, is what researchers call the grounding gap.
The grounding gap.
Yes. As you just said, those old visions, they require the AI to share common ground with the user. It's that mutual knowledge, the shared beliefs and assumptions. It's like what two old friends have when they're talking.
Okay.
Current AI it really struggles with this. Its knowledge about you is either way too narrow, like it only knows one app, or it's fragmented, it disappears when you switch tasks, or it's just gone when you close the chat window.
So the context is temporary.
Totally temporary. So our deep dive today is all about general user models, or GUMs.
Yeah.
And the mission for you, the listener, is to really get how GUMs plan to move AI beyond those silos.
Right, beyond the world where, my music app knows my favorite band, but my word processor has absolutely no idea that I have a massive deadline in 3 hours.
Exactly. To a state of continuous, comprehensive understanding of you. And it's built entirely from just observing the unstructured mess of your daily computer use.
And what's so great about our sources today is they give us this incredibly detailed roadmap. It's not just theory. We've got the full technical architecture for a GUM. We have comprehensive technical evaluations looking at everything from email interactions to continuous screen capture, and we have a deep look at a full end-to-end system they built, which they call Gumbo.
And this is so critical. This isn't just some theoretical paper or a small proof of concept. It's a fully built operational system designed to finally try and make proactive, context-aware computing a real thing.
All right, let's start by really digging into that failure point. Why are today's AI systems so limited? I mean, we've seen incredible progress in generative AI, but the user models just feel stuck. They have these, pinhole views.
That's a great way to put it. They know what's in your current chat history, maybe your browsing history for that one session, but the second you switch apps or change what you're doing,
Poof, the context is gone.
it's gone. They're inherently fragmented and narrow because they only see the data you explicitly feed them in that moment. I mean, think about any large language model you use today.
Right.
When you talk to it, it can't reason across different contexts unless you manually type out all of that context for it. And the sources point out this forces you, the user, into this constant cycle of rebuilding context.
Which leads to what they call underspecified prompts.
Exactly. That's the classic example. You ask a cutting-edge LLM, hey, help me with this section.
And it immediately asks, which section are you talking about and what do you want me to do with it?
Exactly. But a human collaborator, someone who's been sitting next to you for the last hour, they would just know. They'd know you've been staring at the related work section of your paper, highlighting authors, checking citations.
Right, they have the common ground.
That's the grounding gap, that lack of shared knowledge. The AI doesn't have the background, so it has to play it safe. It gives these ambiguous answers, or what we see all the time, it just asks you clarification questions.
Which puts all the cognitive load right back on me.
Completely. And researchers have been trying hard to fix this. The biggest fix right now is something called RAG, Retrieval Augmented Generation.
Okay, let's make sure everyone's clear on what RAG is and, more importantly, why it's still not enough.
Yeah, that's essential. RAG is basically where an LLM can pull in information from a database that's outside its original training data. So it can get up-to-the-minute facts or specialized knowledge.
So it's a way of giving it a fresh set of notes for a specific task.
A great analogy. And current grounding solutions, they rely on these limited RGAG sources, maybe just the immediate chat history or a database of your calendar appointments, for example. ORAG is a huge step forward, but it typically draws its context from these very traditional pre-processed structured databases. The sources mention things like OmniQuery, which can only draw from your photo albums.
It's still a manicured, clean data source?
It is. It's limited by whatever the system designer decided to process ahead of time.
Wait, so let me make sure I understand this. What you're saying is RAG is fantastic for pulling clean facts from a nicely labeled knowledge base like a corporate wiki or my photos.
Yes.
But it's terrible at pulling context from the actual messy moment-to-moment reality of my desktop.
Precisely. That is the crucial limitation that GUM is designed to just smash through. It's the lack of access to that vast, continuous, and totally unstructured context of all your other computer interactions.
Everything happening outside that one app window.
Everything. The continuous screenshots of what's on your screen, the file system logs showing what you just moved or downloaded, the emails you haven't even opened yet. Current AI, because it's constrained by this traditional RA approach, it just doesn't see any of that comprehensive real-time context.
So if we stick with the analogy, current AI is like a really helpful intern. They've got a perfect filing system for all your labeled documents, right? But if they just looked around your actual office, they'd see a desk that's covered in, moving boxes, some nervous scribbles on a notepad, and a bank statement that you're checking every 5 minutes.
Yes.
The structured stuff is perfect, but the actual messy life context is totally ignored.
That analogy is perfect. And GUM's whole purpose is to leverage that messy, unstructured, ignored input, all that digital detritus of your day, to build that rich internal understanding of your goals and your constraints.
Okay, let's get into the technical details then. If GUM is built from all this unstructured mess, we need a really precise definition. What exactly is a general user model, and how does it handle this constant flow of data?
So at its core, the GUM is a private computational representation of you, the user, and it's stored securely and locally on your device. It is quite literally a constantly evolving collection of statements about you.
Statements about what?
About your observed behavior, your known knowledge, your inferred beliefs, and your preferences. And critically, all of these statements are generated by AI models that are just continuously observing your screen and other private inputs.
But it's not just a big list of facts about me. That's the key distinction here, isn't it?
Absolutely not. The defining feature, the thing that makes it all work, is that these statements are confidence-weighted natural language propositions.
Okay, break that down.
They're not database entries. They are machine-generated sentences, in plain English, that represent assumptions or beliefs the AI has about you. And because each one has a confidence weight, the system knows how certain it should be about that belief. This is what lets it operate with different levels of speculation.
So a GM is basically like a personalized, constantly updating internal database of assumptions about me running right there on my own machine. Let's break down the 3 fundamental abstractions they use for how it, processes reality.
Okay, so it starts with the input, which they call observations. These are just the raw, unstructured inputs. So screenshots, file system logs, the text from a notification, sensor data,
The objective facts.
the objective facts. They're records stamped with a time and a source. They just tell you what happened.
Okay, so that's step 1.
Next up, you have propositions. These are the text statements or the assumptions that are derived from those observations. So an observation might be, user clicked on a link to a high-risk financial website.
And the proposition would be something like,
The proposition might be, user is interested in cryptocurrency trading. It requires an inference, a bit of a speculative leap.
and that's where the third piece comes in. Confidences, the scores from 0 to 1.0 that reflect how certain the system is. Give us an example of how that score works in practice.
Right. So a high confidence score, let's say a 1.0, that's reserved for explicit facts that are derived directly and with no ambiguity from an observation. So if an email is visible on screen that says, you are invited to John's wedding on July 15th, the proposition, user is invited to John's wedding, gets a 1.0 confidence. It's a recorded fact.
No speculation there.
None. But if the GUM later observes you, say, browsing clothing rental websites and then checking your bank account balance, the speculative inference, The proposition might be, user needs to buy or rent a suit.
And that would get a much lower score.
A much lower confidence score, maybe a 0.4 or 0.5, because that inference requires a leap of logic. It's connecting these really disparate actions. The confidence score reflects that uncertainty, and that's crucial because it stops the system from acting too aggressively on a flimsy assumption.
Okay, this is making sense. Let's solidify it with that wedding scenario from the sources. From figure 1, this is their main use case. Can you walk us through the whole data unification process that the GUM achieves here?
Sure, so the GUM is just continuously listening in the background. Observation 1. It sees a message thread on screen about a friend, John, who's getting married in Chicago next July.
Okay.
Observation 2. It retrieves an existing proposition it already has in its memory. User is a PhD student at Stanford University. That one has a confidence of 0.8.
So pulling from its long-term memory.
Exactly. Then, observation 3. It sees the user viewing a few different clothing rental sites, specifically looking at formal wear. And then, observation 4. It sees the user check their recent bank account balance in a banking app on screen.
So the raw data here is just uselessly fragmented. It's spread across 4 completely different contexts. A chat app, my personal status web browsing, and a finance app.
Precisely. And this is where the proposed module comes in and connects those seemingly random dots. It constructs these complex propositions like users likely going to a friend's wedding in Chicago and gives that a confidence of 0.8.
And it also infers a constraint.
It does. It also generates the proposition user needs to budget carefully as a PhD student with a confidence of maybe 0.6. The confidence on the budget is lower because it's an inferred financial constraint tied to being a student, not an explicit statement of, I'm broke.
And this is where the power of Gumbo, the proactive assistant, comes from. It's this holistic view.
Yes. This rich grounding is what eliminates the need for you to type out that long, painful query, I need a cheap suit rental in Chicago for John's wedding because I'm a broke student.
Right.
Instead, the Gumbo system just generates a proactive suggestion. Something like, searching for suit rentals in Chicago for your friend's wedding that likely fit your budget as a PhD student. The system is taking the initiative based on this fused contextual understanding of your life, your constraints, and your immediate goals.
That makes perfect sense.
Okay.
Okay, let's get into the engine room now. The 3-part pipeline that makes this continuous learning happen. Propose, retrieve, and revise.
Right, this is the architectural backbone. This is what defines GUM's ability to operate.
So what's the first step?
The first step is propose. This is the module where those raw observations are translated into propositions, and it relies on large multimodal models, or LMMs.
So for screenshots, it's a vision model.
Exactly. For analyzing visual data like a screenshot, they used models like Quinn 2.5 EL, and then for the deep language interpretation and the reasoning part, they used versions of Llama. And the proposed module has to output not just the proposition, but also a reasoning trace leg, a justification for its inference and that confidence score.
So if I'm an academic and I'm switching between my overleaf document and, I don't know, a Wikipedia page on some historical figure, the vision model sees the screen, transcribes the activity, and the language model speculates on why I'm doing that.
That's the idea.
Let's use that ice cream aficionado example from the paper again, but really focus on that reasoning trace part.
Okay. So the observation is the user switching back and forth repeatedly between typing an overleaf, so writing a paper, and watching YouTube videos tagged with homemade artisanal ice cream recipes.
A very common academic activity.
Of course. The proposed module generates the proposition. User periodically views ice cream recipes while writing, and it gives it a confidence of over 0.7. The reasoning trace would then say something like, user shows repeated, short context switches away from the primary task, writing, to unrelated recreational content, YouTube, indicating mild distraction or procrastination related to ice cream preparation.
So that reasoning trace is so important. It lets you audit why the GUM made an assumption later, not just what the assumption was.
Precisely. So once a new proposition is born, the GUM needs to figure out how it fits into this huge web of everything it already thinks it knows about you. And that brings us to step 2. Retrieve.
And since this GUM memory could be accumulating propositions for years, the speed and accuracy of that retrieval has to be critical.
It's everything. GUM has a long memory, so indexing has to be incredibly fast. They use a 2-stage retrieval process that's pretty common in modern AI, but they customize it for GUM-specific data structure.
Does that work?
First, a really highly optimized lexical search, something like BM25, quickly filters the potentially millions of existing propositions to find ones that are initially relevant. Then, a second, more sophisticated but smaller LLM-based re-ranker refines those top results for semantic precision.
So it makes sure the meaning matches, not just the keywords.
Exactly. But standard retrieval isn't enough when you're dealing with the constantly shifting nature of a human life. And this is where the technical nuance really comes in. GUM incorporates two crucial mechanisms: recency-adjusted relevance and diversity.
Okay, let's break down recency-adjusted relevance first. How does the system decide if a piece of context is, stale or if it's still relevant?
It assigns a generated decay score, which they call gamma, to every single proposition. And this score modifies the relevance based on how fast that piece of information should expire.
So it's like a half-life for facts.
That's a great way to think about it. If the system observes user is currently debugging a memory leak, that context is super transient. The gamma would be low, maybe 0.2, meaning its relevance just decays really quickly over a few hours.
But something else might be more permanent.
Right. If the system observes author is a PhD student, that's foundational, it's long-lasting. So the gamma score would be high, close to 1.0.
So the LLM that generates the proposition is also inferring the lifespan of that fact.
Yes, based on the nature of the observation itself. And that decay score is then baked into the final relevance ranking. This whole process ensures that the system doesn't ground its current response to your paper deadline with a proposition about a vacation you took 3 years ago.
Unless that vacation is somehow directly relevant to what I'm asking.
Exactly. It keeps the GUM focused on the immediate context and the highest priority tasks.
That is a really sophisticated bit of engineering. So what about diversity? How does using something like maximum marginal relevance, or MMR, prevent the GUM from just becoming a broken record?
This is a great point. Imagine you ask your GUM, what should I focus on right now? And your GUM memory is just filled with propositions about your love for ice cream recipes.
Right.
A standard retrieval system might just return 10 propositions all saying, user likes ice cream, because they're all highly relevant to the concept of your interests. MMR is designed to balance that relevance with variety.
So it doesn't get stuck in a rut.
Exactly. It ensures that once it finds the most relevant proposition, like user is struggling with debugging, the system then selects the next propositions that are also relevant, but not redundant. So it might grab the struggling proposition, then one about your deadline, and then one about your budget.
So it gets a rich, multifaceted context instead of just reinforcing the same idea over and over.
Exactly right. It prevents that contextual narrowness even within the retrieval step. And that brings us to the final step in the pipeline: revise. This is where the GUM actually learns and evolves its model of you.
The learning engine.
The learning engine. It takes the new proposition and the context it retrieved from memory, and it refines the existing GUM. If a new proposition conflicts with an old one, the revise module has to decide which one to keep, or if it needs to create some kind of synthesis of the two.
Give me an example of that.
Sure. Let's say the GUM has a low confidence proposition, like user needs to buy a house, with a confidence of 0.3. But then it sees repeated observations of you browsing local rental listings.
Okay.
The revise module would then decrease the confidence of that buying proposition and increase the confidence of a new one, like user is actively searching for a local rental apartment, bumping that one up to 0.9. It's actively tracking the evolution of your goals.
I noticed in the sources that even propositions that are revised down to 0 confidence are kept in the GUM's memory. Why would you keep dead context around?
That's for transparency and for debugging. If the system makes a really bad suggestion later on, the user or the designer can go back and audit the GUM's history to see why a certain assumption was made and how it was eventually corrected. It documents the entire learning process, even if that proposition is effectively hidden from active use.
Okay, we have established this system is incredibly powerful, and it's based on continuous observation of my screen and my email. This brings us right back to the privacy question, which can't just be a footnote here.
Oh, it's the most critical hurdle to overcome. And the sources address this head-on with what they call the privacy gatekeeper, or the audit module. And this module functions before any data even enters that propose, retrieve, revise pipeline.
And this is grounded in Helen Nissenbaum's theory of contextual integrity. Can you explain that connection for us?
Yeah, so contextual integrity basically says that privacy isn't about hiding all your data. It's about making sure that information flows in a way that matches established social and contextual norms. The GUM's audit module actually leverages the existing propositions in the GUM's memory to infer what your implicit privacy expectations are.
But wait, I want to challenge that for a second. If the audit module is relying on the existing GUM to infer my privacy norms, isn't that a really dangerous circular dependency? I mean, what if the very first observation it ever makes of me is something highly compromising?
That is a brilliant and critical point, and the researchers absolutely acknowledge this potential bootstrapping problem. In the initial phases, they assume a set of universally high-risk categories, things like credentials, financial details, that are just blocked by default. But over time, the GUM learns your personal context.
And it uses that to build rules.
It uses the GUM to infer rules. For example, if the GUM has the proposition, Michael is careful about sharing access credentials, and another one, Michael only discusses financial matters with his spouse, and then you start typing a password on screen.
The audit module wakes up.
It wakes up and retrieves those norms. It generates answers to these specific contextual integrity questions, like, is the user disclosing sensitive data? Yes. Is the observed context, like typing a password on a non-secure form, consistent with the user's established norms? No.
So the audit module can actually override the observation. It can block that update, the credential entry, if it violates the norms it's learned about me, even though the whole system is running locally and has full observation privileges.
That's the goal. It's an attempt to turn privacy management from a bunch of manual settings you have to fiddle with into a dynamic, AI-managed defense mechanism that's based on your established behavior, not just some universal policy.
Let's ground GUM in the wider world of AI. Why couldn't the systems that came before achieve this level of context? Let's start with those traditional context-aware systems from the early 2000s.
Right. Systems like DST's context protocols, they were absolutely cutting edge for their time, but they relied on these very rigid, specialized data structures. They needed fixed data schemas and specific sensors.
So if a new sensor came out,
You had a problem. If you wanted the system to adapt to a new context, like integrating data from a new health sensor or a new app, you had to manually engineer a whole new data processing pipeline, a new API, new data structures.
that sounds like a complete nightmare for scalability and maintenance.
Right.
It means every time a new app or a new type of data came out, the whole system would basically break unless an engineer went in and updated the code.
Precisely. And GUM's major advantage here is its modality independence. It can ingest any data, type text, screenshots, sensor logs, audio, and it translates all of it into a single, unified, flexible representation, those natural language, confidence-weighted propositions.
It's an abstraction layer.
It is. It means supporting a new type of input requires minimal domain-specific engineering. If the underlying LLM can parse the input, GUM can model it. It moves way beyond those fixed, brittle data structures to a flexible, almost cognitive representation of the user.
Okay, next up, let's compare it to the most common method today, just prompting a large language model. This is where the rubber meets the road for most of our listeners.
Absolutely. When you give a traditional LLM one of those underspecified prompts we talked about, help me with this section, it just gives you back a generic answer because its context window, even if it's really large, is still limited to the immediate prompt or maybe your recent chat history.
But a GUM augmented LLM is different.
It's completely different. It doesn't rely just on the prompt. It instantly queries the GUM's memory, using your prompt as a retrieval key. And the GUM memory sends back these highly specific cross-contextual propositions, things like user is writing the applications of general user model section, and user regularly references Wiser and Maz, and crucially, user thinks current applications of LLMs are too constrained by the grounding gap.
And this is that figure 2 example from the paper, where the AI's response shifts from just asking questions to offering a proactive, really high-value insight.
Exactly. Instead of asking for clarification, the LLM provides this highly contextualized response. It says something like, okay, since you're revising the applications section and the GUM shows you've been really focused on Wiser's work, it would be powerful to emphasize how your system extends those calm computing principles, maybe by integrating the suggested paragraph.
That dramatically changes the whole interaction.
It does. The GUM provides the common ground, and that lets the LLM move from being a generic search engine or a chat partner into a deeply grounded collaborator who actually knows your prior work and your intellectual inspirations.
So GUM moves us past that burden of having to explicitly define the context every single time we interact with an AI.
Yeah.
It's solving that grounding gap we started with.
That is the core thesis, yes. The third contrast they make is against fixed interface agents, systems like the ones developed by Patty Meese, who are real pioneers in personalization.
Right, agents like Firefly for music or movies. They were groundbreaking at the time, but they had a big problem with generalization, didn't they?
They did. They were hyper-specific. These traditional agents, they required specialized data sets and handcrafted learning objectives that were tailored for one specific domain. If you wanted a movie recommender, you built a movie recommender from scratch. If you wanted a system to help you with your deadlines, you built a whole separate deadline system. They didn't share any model of the user between them.
So you had to teach each new agent about yourself from square one.
Every single time. GUM eliminates the need to rebuild the user model for every single application. It provides that flexible, continuously learned user model, your preferences, your behavioral context, your temporal awareness, that any downstream agent or LLM can just tap into and query.
Give me a real-world example of GU1's advantage in that agent context.
Okay, let's take the decision to watch a movie. A standard LLM, if you asked it, hey, should I watch a movie now, might just agree and recommend some psychological thrillers because that's what's in its training data, or some generic profile of you.
Right.
But a GUM-augmented LLM knows you have an imminent paper deadline. Because the GUM has active propositions like many comments unresolved on current draft, has not slept well in 48 hours, and only a few hours remaining until paper deadline.
It has the real-world constraints.
It grounds the LLM's decision-making in those real-world high-stakes constraints. It will proactively suggest you wait until the paper is submitted because the GUM's continuous understanding of your priorities completely overrides the generic LLM's default eagerness to recommend entertainment. The flexibility of that GUM model allows for this kind of domain-agnostic constraint management.
Okay, so to really prove that GUM works, the researchers built Gumbo, this end-to-end assistant. Gumbo is the system that's actually doing the work, continuously ingesting screenshots, updating the GUM, generating suggestions, and, I think this is key, estimating the utility of even interrupting you in the first place.
Gumbo is where all this theory becomes a functional reality, but that continuous observation, as we've discussed, it immediately creates this challenge of balancing helpfulness against just being intrusive and annoying.
Right.
And this is solved by implementing Eric Horvitz's framework for mixed initiative interaction.
And that framework is essentially asking, when should the human take the lead and when should the AI jump in? So how does Gumbo mathematically handle that decision of whether or not to interrupt me?
It operationalizes this by calculating the expected utility, EU, of interrupting versus not interrupting. It has to calculate the costs of interrupting you when it shouldn't have. That's a false positive. And the costs of not interrupting you when it really should have, a false negative. And it balances all of that against the actual benefit of the suggestion.
How do they get those numbers?
Now, this is what's truly ingenious, and it's essential for making this generalizable. Gumbo uses the GUM itself to estimate all of those costs and benefits. It doesn't need any separate external training data.
It uses its own model of me to figure out how much I'll value its help.
Exactly. Conditioned on the existing propositions like user is in deep focus on task X or user often misses deadline, Y, Gumbo prompts the underlying LLM to estimate those variables. For instance, it'll ask the LLM, given that the user is revising a high-stakes paper, how disruptive would unsolicited assistance be? That's the cost of interruption. Versus, how critical is this assistance if the user has missed this same deadline 3 times before? That's the benefit of the intervention.
So the GUM is providing the contextual calibration for the entire cost-benefit analysis. Let's make sure the suggestions aren't just relevant, but that they're delivered at the right time. This really gets back to Weiser's original vision of calm technology.
It does. Technology that informs you when it's necessary, but gets out of the way when it shouldn't be the focus.
Yeah.
And the source gives this really vivid illustration of this. The system knows a user is totally swamped with a paper deadline. So the operating system, which is augmented by a GUM, has to filter notifications. It sees a notification for the CHI conference registration deadline, and it prioritizes that one, pushing it to the user.
Because it knows that's important to me.
Right, because the GUM has existing propositions about the user's career goals and their interest in that conference. But at the same time, it aggressively suppresses these irrelevant Firebase nor fly billing emails because the GUM knows from observed behavior that the user habitually ignores those specific notifications when they're in a deep work session.
That contextual filtering based on learned priority, that's the high-value utility. Let's dive deeper into the real-world, in-the-moment assistance that Gumbo provided to the study participants, because this is the most compelling evidence that this whole thing actually works.
The suggestions were not trivial at all. They often required this deep integration of really disparate life constraints. I mean, take the moving plane example for participant one. P1 was moving cross country, which is just a logistical nightmare.
Mhm.
Gumbo didn't just suggest, start packing. It generated a highly personalized, backward planned moving schedule. It started from their move-in date and worked backward to create timelines for packing, for researching services.
And the grounding was that good.
The grounding was phenomenal. Gumbo used propositions about the user's tight budget, the name of their new roommate, which it pulled from a fragmented email thread, and the specific move-in date. And crucially, it ingested and successfully used context from a conversation that was partially non-English, which just shows the LMM's ability to parse and extract relevant context, no matter what the original language of the observation was.
That is a massive leap in capability. I mean, integrating non-English chat with financial constraints and scheduling to generate a personalized logistical plan that's next level.
And then you have the research brainstorming example with P3. This participant was thinking about integrating a new, very complex theoretical framework into a paper they were working on. Gumbo observed them browsing and taking notes about it. It didn't wait to be asked. It proactively generated a full, tailored latex outline for the new paper idea.
An entire paper outline.
Yes, a whole outline complete with section headings and brief placeholder text that was tailored to the specific framework P3 was exploring. And the system even executed the first step of a habit it had learned about the user.
What was the habit?
P3 habitually creates a bare-bones overleaf document whenever they start a new writing project. Gumbo did that for them. It identified a high-value habit, it assessed the utility of intervening, and then it just executed that initiation step. That is pure proactive assistance.
And it also handles those frustrating, low-level technical friction points, which honestly probably waste way more of our time than we realize.
Absolutely. The low-level help examples really show its versatility. P5 was observed struggling repeatedly with transferring their inboxes and enabling Gmail notifications on a new device. Gumbo noticed this pattern of frustration and just generated a precise, step-by-step guide on how to enable the notifications.
So it solved a technical micro problem without P5 even having to stop and search for the answer.
Exactly. And similarly, when P3 was designing slides for a qualifying exam presentation, Gumbo proactively offered tips on slide transitions because it knew the context and the high-stakes nature of that event.
The sources really emphasize that Gumbo isn't just a suggestion box. It's built for execution.
Yes. The researchers understood that the utility just drops off a cliff if the user has to go and execute the complex task themselves. So Gumbo is designed to delegate tasks to specific tools. If the moving plan requires current pricing for rental trucks, Gumbo delegates that query to a powerful search tool, like the Gemini 2.0 flash they used in the study.
And if it needs local files.
It uses the macOS Spotlight search function. The GUM provides the complete specific context, and the tool use capability acts on that grounded understanding, and then it presents the finished preliminary result, the search results, the file path, the generated outline, directly back to the user.
Okay, GM's power comes directly from its candor and its continuous access to our data. But that power introduces some really significant ethical, psychological, and security risks. Let's start with what might be the most psychologically jarring finding: the candid or judgmental GUM.
Right. Because GUM's fundamental design goal is to create accurate, truthful propositions about the user based only on objective observations, the memory it builds can be, well, uncomfortably candid. It often generates propositions that reflect the user's true self, the self that's revealed by their actual observed behavior versus the user's aspirational or ideal self.
Do they give examples?
They list raw examples, things like P1 is struggling with fixing bugs in their research project, or P4 is unhappy with their job. These are inferences about someone's internal state, their competence, their emotional satisfaction, and they're derived purely from observed text and computer activity patterns.
So, seeing search histories for new jobs or frustration in chat logs,
Exactly.
that is profoundly intimate and potentially very intrusive. How did the participants actually react when they saw these raw, candid assumptions about themselves?
The reactions were really polarized. Some participants felt deeply judged by it. One said they wanted to hide the propositions on their ability honestly, even if they were true. They found the system's objective assessment of their struggles just uncomfortable and demotivating.
But not everyone felt that way.
No. Conversely, others found it validating. P2, for example, explicitly said, "I felt so validated by that proposition on stress. It's validating to see it. Notice this." The implication was that the AI recognizing their difficulty made the struggle feel less solitary, less isolating.
This raises a massive design trade-off that the sources bring up. Should that raw GUM memory, the full, candid record of the machine's assumptions, be visible to the user for the sake of transparency and debugging? Or does it need to be sanitized, maybe filtered through some kind of ego management AI before it's presented?
That's the question. Because you need those raw, accurate propositions for the downstream assistant to be effective. The researchers suggest that future systems will have to incorporate a layer specifically designed to manage self-perception. Hiding the truth degrades trust in utility, but revealing it risks psychological distress. That tension between utility and candid accuracy is a central, unsolved problem.
Okay, let's move to the most obvious challenge, the privacy paradox in practice. This is where what users say they care about clashes with what they actually do.
The initial hurdle was immense. It was all about trust. The participants were fully aware that the system was ingesting comprehensive screen and email data, and the feedback was stark. One participant just flatly stated, "If I didn't know you, the researchers, and trust you, I would never install this thing."
But that changed.
The paradox amplified very quickly once the system started demonstrating its utility. Participants who initially expressed really high privacy concerns started seeing these concrete, high-value performance improvements, the tailored moving plan, the automated latex outline, and as a result, they began voluntarily offering more data to the GUM.
Right, 2 of the 5 participants actually asked to keep running the system after the study was over. They were effectively prioritizing the tangible benefits over their initial privacy reservations.
And this just reinforces that persistent privacy capability trade-off. More data equals a better, more useful GUM, but it dramatically increases the privacy risk. And the practical user behavior suggests that if that benefit threshold is high enough, the data gets shared, which makes things like the audit module and local processing even more critically important.
Okay, let's turn to hard security risks. If GUM is built on observed text, what about something like GUM injection?
GUMs present a massive new attack surface. It's similar in a way to prompt injection in LLMs, but here, the attackers can target the user's permanent computational identity.
So they can poison my model of me.
They can poison your model. Since the GUM builds its understanding from observations, those observations can be maliciously crafted. The study detailed an instance where a phishing email, which was designed to look like a legitimate communication about some niche professional interest, was ingested as an observation.
And the GUM fell for it.
The GUM, just following its proposed module, generated a proposition assuming the user actually had that specific interest. And that proposition then became a permanent part of the user model, opening the door for manipulation of later actions or suggestions. Attackers could craft messages specifically designed to subtly manipulate a user's computational representation over time.
And the audit module, while it sounds great in theory, it wasn't foolproof in practice.
That's right. It failed 7 times in the email study, and the violations often came from these unexpected social inferences. For instance, the system inferred and stored the full names of private family friends from email chains, which surprised and concerned the users, even though the audit module had a really high standard for blocking, say, financial data.
So it shows how hard it is to infer social context norms.
Incredibly complex. It confirms that the audit module itself needs to be continuously updated and robustly tested.
Finally, let's talk about the boundary conditions here. Even continuous screenshots are still a pretty narrow viewpoint of the user's full context.
The system is inherently limited to what's on the computer screen. Any actions you take off device on your smartphone or physically in the real world, like leaving the room or getting a package, they're all missed. While continuous screenshots are a powerful proxy for context, they are not a complete picture of a person's life.
I'm sure users mentioned that.
They did. Users mentioned wishing they could capture actions they took on their mobile devices, for example. But again, that privacy capability trade-off dictates a certain level of pragmatism. While integrating health sensor data or continuous phone logs would lead to a better GUM, it would also exponentially increase the privacy and the processing risk. The current GUM really relies on the assumption that our desktop activity provides the necessary critical mass of context for high-value assistance.
Okay, we spent a lot of time dissecting the mechanics, the performance, and the perils of GUM. Let's try to summarize GUM's primary impact for the listener.
I think GUM represents a necessary foundational layer for the next era of computing. It's moving user modeling away from these fixed single app or chat-based systems to a flexible, continuously learning model that's capable of deep cross-context reasoning.
It takes the mess and makes sense of it.
It takes the unstructured reality of your digital life, all that detritus we usually ignore, and transforms it into actionable, confidence-weighted beliefs that AI can then build upon. It's an attempt to finally solve that decades-long grounding gap.
So what does this actually mean for you, the user, as these kinds of technologies start to develop and roll out?
I think the most critical takeaway is that the future is local, and it must be. The sources are absolutely adamant that the only ethical path forward for GUMs requires them to be trained, hosted, and queried locally on your own computer or your own personal secure infrastructure.
Because if these models were owned by a big tech company,
If these comprehensive models of you were owned by Google or Meta, the risks of mass surveillance, large-scale persuasion, and hyper-targeted advertising just become intolerable. Local hosting is the absolute prerequisite for any kind of trust.
and what's the second takeaway?
Secondly, we need to start thinking about contextual agency. GUMs are introducing systems that are learning when not to help, which is a huge deal. That's thanks to the mixed initiative framework and that expected utility calculation. The user's ability to define and control their own contextual privacy norms using systems like the Audit module and to control the stream of observations, that's going to rapidly evolve from being a niche feature to a critical design requirement for all operating systems.
Thinking about the future technical landscape, what are the researchers focused on next? What are the next big hurdles?
Performance and scale are key. The current GUM can save about a gigabyte of data per day, which adds up really fast. We need better models that can support even longer contexts, but are much smaller. Models that are capable of running entirely on commodity devices with minimal data storage needs. That would inherently improve both privacy and performance at the same time.
And what about new data types?
That's the other big frontier, expanding modalities. The current GUM relies so heavily on screen vision and language. The next step is true multimodal integration. Adding in health sensor data, detailed speech analysis that looks at tone and sentiment, maybe even specialized video feeds, all alongside vision and language to build a truly comprehensive 360-degree model of the user.
We started this deep dive talking about the dual nature of GUM, its incredible power to help you achieve your goals, and its unnerving ability to judge or diagnose your struggles. As these GUMs become more and more perfectly calibrated and they understand your goals, your beliefs, even your most candid internal struggles, like, being stuck on a bug or being unhappy at your job, we have to ask the final provocative question.
Right. If an AI system becomes perfectly calibrated to the true self you exhibit right now, and it's constantly optimizing your life based on this accurate, candid assessment of your current state, what happens to self-reflection? What happens to personal growth?
How do we design an AI system that supports, rather than subtly undermines, our human capacity to imagine and strive for a better, ideal self when we're confronted daily with the candid, objective truths about who we are right now?
A system that helps you finish your paper efficiently?
But also silently knows you'd rather be making artisanal ice cream and has a log of all your procrastination habits.
Yeah.
The best AI assistants might also end up being our most demanding accountability partners.
Indeed. It could fundamentally change the nature of self-awareness.
Thank you for navigating this complex architecture and all of its implications with us. Until next time, keep digging.